So you're listening because you want to, connect the dots, really get how the physical world works, but without getting totally bogged down in like all the tiny details.
Exactly. You want those aha moments.
Right, where it just clicks.
Yeah.
And that's pretty much what we're doing today. We're taking a deep dive into fundamental physics.
Yeah, we've got this great overview, and we're basically pulling out the key ideas.
Stuff that explains, well, everything from why an apple falls
To how the entire universe got started. It's about building that foundational understanding, really getting the principles behind motion, forces, energy.
Heat, waves.
Electricity, magnetism, even nuclear physics and space. It's quite the tour.
It sounds like a lot, but we're aiming for that core understanding, yeah.
That's the mission, the fundamental rules.
And it all kind of kicks off with measurement, doesn't it? Physics needs numbers.
Absolutely. I mean, think about it. Rulers, micrometers for really tiny things.
Measuring cylinders for liquids.
Yeah.
Or even using water displacement for like a weirdly shaped rock.
Right. And clocks, obviously. Getting better and better at measuring time. It all comes back to observing carefully and measuring accurately.
And a really basic but super important idea is the difference between just a quantity.
Like distance, how far you walked.
Yeah. Versus a quantity that also has direction, like displacement.
Or speed versus velocity, same idea. Velocity tells you speed and which way you're going. Scalars versus vectors.
That direction part is crucial. Telling someone walk 5 meters isn't very helpful.
Not really. 5 meters where, that's the vector part.
And these vectors, these directional things, they add up in specific ways.
Yeah, if you've got two forces pulling at right angles, you can picture the result, right?
Like the diagonal of a box.
Exactly. And we can actually calculate it precisely using things like Pythagoras' theorem or trig.
Okay. So math gives us the exact answer for that combined effect.
Precisely. Magnitude and direction.
Okay, so building on vectors,
Yeah.
motion itself. You mentioned speed and velocity.
Right. Speed is just distance over time, meters per second. Velocity is displacement over time, so it includes direction, still meters per second.
And acceleration.
That's how quickly the velocity changes. So speeding up, slowing down, even changing direction counts as acceleration, measured in meters per second squared.
And keeping those units straight is pretty important in the calculations, I guess.
Oh, vital. Otherwise, the numbers just don't make sense.
One thing I always liked was seeing this stuff on graphs.
Yeah, the graphs are great. A displacement time graph.
The slope tells you the velocity, right? Flat line means stopped, straight line means constant speed.
And a curve means acceleration. If the line goes down, you're heading back.
And then velocity time graphs.
The slope there is acceleration. Constant slope, constant acceleration. And the area under that graph...
That's the total distance you traveled.
Yep. Really powerful visual tools for understanding motion.
Oh, what about things just falling? Gravity.
Right. Well, in a perfect vacuum, everything accelerates down at about 9.8 meters per second squared. We call that G.
But we don't live in a vacuum.
Exactly. So you have air resistance or drag. As something falls faster, the drag pushing up increases.
Until
Until it balances the force of gravity pulling down. At that point, the net force is zero.
So no more acceleration.
Correct. The object keeps falling, but at a constant speed. That's terminal velocity.
Huh. It's funny how just falling involves all that, and it brings up mass versus weight, too. They're not the same.
Definitely not. Mass is the amount of stuff in an object measured in kilograms. It doesn't change wherever you are.
But weight does.
Weight is the force of gravity on that mass, so it depends on the gravitational field. You weigh less on the moon because its gravity is weaker. Weight is a force measured in newtons.
And the link is W equals mg, weight equals mass times gravitational field strength.
That's the one. Simple but fundamental.
Okay, another property of stuff is density.
Yeah, how much mass is squeezed into a certain volume? Kilograms per cubic meter.
And that decides if something floats or sinks.
Pretty much. If an object's density is less than the fluid it's in, it floats. We measure density using balances and measuring cylinders, or displacement for solids.
Got it. Now, forces. They don't just make things move, they can also change their shapes.
Like stretching a spring. That's where Hooke's law comes in. Force equals the spring, constant times the extension, F equals XAX. Within limits, of course.
K tells you how stiff the spring is.
Exactly. But the really big deal with forces is changing motion. Newton's laws.
The big three.
Foundational stuff. First law, inertia. An object stays doing what it's doing resting or moving steadily unless a force acts on it.
Things like to keep doing what they're doing.
Basically, yes. Second law, F. A. Sharma. Force equals mass times acceleration. This tells you how much the motion changes. More force means more acceleration, more mass means less acceleration for the same force.
And that force has to be the net force, right? The overall result.
Crucial point. It's the resultant force that matters. And for something to move in a circle, you constantly need a net force pulling it towards the center.
Like swinging a ball on a string.
Yep. We also need to remember friction or drag in fluids. It always opposes motion.
Forces can also make things turn, like using a wrench.
That's the moment of a force. It's the force multiplied by the perpendicular distance from the pivot.
And for balance, clockwise moments equal anti-clockwise moments.
That's equilibrium. And related is the center of gravity, the point where all the weight seems to act. Lower center of gravity, wider base, more stable.
Like a racing car versus a truck.
Good example. Stability matters.
Okay, another concept. Momentum.
Mass in motion. PEFWMV, kilograms meters per second.
And impulse.
That's the change in momentum. It equals the force applied multiplied by the time it acts for. F delta T.
What's the big idea with momentum?
Conservation. In any collision or explosion, if no external forces act, the total momentum before is the same as the total momentum after.
Like a cannon firing a cannonball.
Exactly. The cannon recoils backward with momentum equal and opposite to the cannonball's forward momentum. Total stays zero, assuming it started at rest.
Right. Let's switch gears slightly to energy. So many types.
There are. Kinetic energy, energy of motion. Potential energy, stored energy, like gravitational or elastic in a stretched spring. Chemical, nuclear, thermal.
And we have equations for some, like kinetic energy is half mv squared.
EK_mv_VOU, yeah. And gravitational potential energy is mE, mass times gravity times height. Or the change is mv times the change in height.
And the huge principle is conservation of energy.
Absolutely fundamental. Energy can change form, potential to kinetic as something falls, for instance, but the total amount in a closed system always stays the same. It's never created or destroyed.
You can track this with energy flow diagrams, like Sankey diagrams.
Yeah, they're great for showing where the energy goes, including the wasted energy, usually heat. But even that isn't truly lost, just less useful.
So what's work done?
In physics, work is energy transfer due to a force acting over a distance. W/eV/d. It's measured in joules, same as energy.
So doing work changes the energy of something.
Precisely. And power is just how fast you do work or transfer energy. Power is energy divided by time, or work divided by time. Measured in watts.
More power means faster energy transfer.
Yep. A 100-watt bulb uses energy faster than a 60-watt bulb.
Okay, where does all this energy come from? The resources.
Well, a huge range. Fossil fuels, coal, oil, gas, biofuels, nuclear fuels like uranium, then renewables. Hydropower from water, geothermal from Earth's heat, solar, wind.
Each with pros and cons, right?
Yeah.
Reliability, pollution, cost, whether they run out.
Exactly. Things like fossil fuels are reliable but pollute and are non-renewable. Solar and wind are clean, but intermittent, depends on the weather.
And most of it ultimately traces back to the sun.
The vast majority, yeah.
No.
Directly like solar power, or indirectly like fossil fuels, which are ancient stored sunlight, essentially, or wind, driven by solar heating differences.
And when we use energy, we talk about efficiency.
Right. How much useful energy you get out compared to the total energy you put in, as a percentage.
Can't be more than 100% because of conservation.
Never. There's always some energy converted to less useful forms, often heat due to friction or resistance.
One last thing in this section, pressure.
Force spread over an area, P equals FA, measured in pascals.
So sharp knife cuts better because the force is on a tiny area, high pressure.
Exactly. And in liquids, pressure gets bigger the deeper you go.
Why is that?
Because there's more weight of the liquid above pushing down. It also depends on the liquid's density. Denser liquid, more pressure at the same depth.
Yeah, okay. Okay, that wraps up mechanics and energy basics. Let's move to heat. Thermal physics.
Sure. It starts with the kinetic particle model, the idea that everything's made of tiny particles that are always moving.
Solids, liquids, gases.
Right. In solids, particles are packed tightly in a lattice, just vibrating. Strong forces hold them.
Liquids.
Particles are still close, but can move around, slide past each other. Weaker forces.
And gases.
Particles are far apart, moving randomly and quickly. Very weak forces between them.
And we can actually see evidence of this, Brownian motion.
Yeah, that random zigzagging of smoke particles or pollen grains in water, that's them getting knocked around by the invisible moving air or water molecules. Direct evidence.
And temperature is linked to this motion.
Temperature is a measure of the average kinetic energy of the particles. Hotter means faster average movement.
which leads to absolute zero, the coldest possible temperature.
Theoretically, yes. And again, at 273 degrees Celsius, or 0 Kelvin, the point where particles would have minimum kinetic energy, the Kelvin scale just starts there. Tk equals T degrees C plus 273.
And this particle motion explains gas pressure, too.
Definitely. Gas pressure comes from all those particles constantly hitting the walls of the container. Billions of tiny collisions add up.
So more hits or harder hits means more pressure.
Exactly.
Hmm.
If you heat a gas in a fixed box, particles move faster, hit harder, and more often pressure goes up. If you squash the gas into a smaller volume at the same temperature, they hit the walls more often, pressure goes up again. PV equals constant if temperature is fixed.
Heating things also makes them expand?
Generally, yes. Thermal expansion. As particles get more energy and move more, they take up slightly more space, pushing each other further apart on average.
Solids, liquids, gases all do this.
They do, but gases expand the most, then liquids, then solids for the same temperature rise, usually. Think of gaps left in railway tracks or bridges to allow for this, or how a thermometer works.
Right. What about how much energy it takes to heat something up? Specific heat capacity.
Yeah, that's SIA in the equation, VLM-ASAT. It's the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius.
So water has a high one. Takes a lot of energy to heat water.
Very high, which is why it's used in cooling systems and why coastal areas have milder climates. It resists temperature changes.
And thermal capacity is just MC, for the whole object.
Yep. Energy needed to raise the whole object's temperature by 1 degree.
Okay, what about changing state? Melting, boiling.
These involve energy transfer too, but the energy goes into breaking the bonds between particles, not speeding them up. That's why temperature stays constant during melting or boiling.
Like ice melting at 0 degrees C. The temperature doesn't rise until it's all water.
Exactly. That energy absorbed during the phase change is called latent heat.
And evaporation, that's different from boiling.
Yes. Evaporation happens at the surface, at any temperature. The fastest particles have enough energy to escape, leaving the cooler ones behind. That's why evaporation causes cooling. Think sweat.
Boiling happens throughout the liquid at a specific temperature.
Right. And factors like temperature, surface area, and airflow affect how fast evaporation happens.
So latent heat is the energy for these phase changes, E equal mL.
Correct. Specific latent heat of fusion, for melting freezing, and vaporization, for boiling condensing. L is the energy per kilogram needed for the change.
If you graph temperature against time while heating ice all the way to steam, you see flat sections during melting and boiling.
You do. Those plateaus show where the energy is going into the phase change, not raising the temperature.
How does heat actually travel? 3 ways.
3 main ways: conduction, convection, and radiation.
Conduction is through solids, particles bumping into each other.
Primarily, yes. Vibrations passed along the lattice. It's much better in metals because they also have free electrons that can carry energy quickly. Poor in liquids, and especially gases.
Convection, that's in fluids?
Liquids and gases. When you heat a fluid, it expands, becomes less dense, and rises. Cooler, denser fluid sinks to take its place, setting up a convection current, like boiling water or room heaters.
And radiation.
That's heat transfer by electromagnetic waves, mainly infrared. Doesn't need a medium. That's how heat reaches us from the sun. Dark, matte surfaces are good emitters and absorbers. Shiny, light surfaces are poor ones.
So heating a pan uses conduction through the metal, convection in the food.
And radiation from the burner. All 3 often happen together.
Okay, let's move on to waves. What's the fundamental idea?
Waves transfer energy but not matter. Think of ripples on a pond. The water moves up and down but doesn't travel across with the wave.
And they have properties like amplitude, wavelength.
Amplitude, maximum displacement, wavelength, distance between crests, frequency, waves per second, and speed. They're related by V equals F. Speed equals frequency times wavelength.
And there are 2 main types, transverse and longitudinal.
Yes. Transverse waves, like light or waves on a string, oscillate perpendicular to the direction of energy travel. Longitudinal waves, like sound, oscillate parallel to the direction of energy travel. Think compressions and rarefactions.
Right. And wavefronts are lines joining points in phase.
Like connecting all the crests, useful for visualizing wave propagation.
How do waves interact with things? Reflection.
Bouncing off a surface. Angle of incidence equals angle of reflection. Frequency, wavelength, speed stay the same.
Refraction.
Bending as a wave enters a different medium and changes speed. Frequency stays the same, but wavelength changes. It bends towards the normal if it slows down, away if it speeds up.
And diffraction.
Spreading out as waves pass through a gap or around an obstacle. It's most noticeable when the gap size is similar to the wavelength. Frequency, wavelength, speed stay the same in the same medium.
Can we see all this easily?
A ripple tank is perfect for it. You can set up barriers to see reflection, change water depth for refraction, and use gaps for diffraction. Really clear demonstrations.
Let's focus on light waves. Reflection from a mirror.
Plane mirror follows the law, IR. It forms a virtual image, looks like it's behind the mirror, same size, upright, but laterally inverted, left and right swapped. We use ray diagrams to track the light path.
Refraction is key for lenses, right?
Absolutely. Light bends, changing speed between air and glass, for example. Refractive index N measures how much it slows down. Snell's law relates the angles and refractive indices. N in sin, I sin R.
And total internal reflection.
That happens when light goes from a denser medium, like glass, to a less dense one, like air, at a large enough angle beyond the critical angle. Instead of refracting out, it all reflects back inside.
Which is how optical fibers work.
Exactly. Light bounces along the inside of the fiber, carrying information over long distances with little loss, used in communications and medical endoscopes.
What about lenses themselves, converging and diverging?
Converging lenses, convex, bring parallel light rays to a focus. They can form real or virtual images depending on object distance, used in cameras, projectors, magnifying glasses, correcting long-sightedness.
Diverging lenses?
Concave spread parallel light out, always form virtual, upright, smaller images, used to correct short-sightedness.
And prisms splitting white light. Dispersion.
Yeah, white light is a mix of colors. When it enters a prism, different colors, wavelengths, refract by slightly different amounts because their speeds in glass vary slightly. Red bends least, violet most, creating the rainbow spectrum ROYGBV.
Monochromatic light is just one color.
One wavelength, yes. It wouldn't disperse in a prism.
Light is part of a bigger family, the electromagnetic spectrum.
It is. A whole range of transverse waves, all traveling at the speed of light in a vacuum, none needing a medium.
What's the order?
From longest wavelength to shortest. Radio waves, microwaves, infrared, visible light, the bit we see, ultraviolet, X-rays, gamma rays. As wavelength decreases, frequency and energy increase.
And they all have uses and dangers.
Definitely. Radio microwaves for communication, infrared for heat sensing and remote controls, visible for sight. UV causes tanning, but also skin cancer. X-rays for medical imaging. Gamma rays for sterilizing and cancer treatment. Higher frequencies tend to be more hazardous.
You mentioned communication. Satellites.
Microwaves are used. Geostationary satellites stay above 1 point on Earth, good for broadcasting. Low-orbit satellites move faster, used for imaging and some communication.
And mobile phones, Wi-Fi.
They use radio waves or microwaves too. Optical fibers use visible or infrared light. It's all about transmitting information.
Digital versus analog signals.
Digital signals are pulses, on-off, 1SDs, while analog signals vary continuously. Digital is generally better, less prone to noise, can be easily regenerated, more data capacity.
Okay, let's switch to sound waves. Longitudinal, need a medium.
That's right. Loudness relates to amplitude, pitch relates to frequency.
How do we measure its speed?
Often using echoes. Measure distance to a wall, time how long for a collapse echo to return. Speed is distance divided by time, remembering the sound travels there and back.
And speed varies in different materials.
Yes, faster in solids than liquids, slowest in gases. Because particles are closer and interact more strongly in solids, transmitting the vibrations quicker.
Humans hear between 20 hertz and 20,000 hertz.
Roughly. Above that is ultrasound.
What's ultrasound used for?
Things like sonar mapping seabeds or finding submarines. Also, medical imaging, like pregnancy scans, because it reflects off different tissues. And checking materials for internal flaws.
And sound waves are compressions and rarefactions. Squeezed bits and spread out bits.
That's the nature of longitudinal waves, yeah. The medium gets compressed and stretched along the direction the wave travels.
Right. Let's tackle electricity and magnetism, starting with basic magnets.
Okay, north and south poles. Opposites attract, likes repel. Some materials are magnetic, iron, steel, nickel, cobalt. Others aren't.
You can make magnets. Induced magnetism.
Yeah, by stroking a piece of iron with a magnet or using a coil with DC current. Soft iron makes a temporary magnet, steel makes a permanent one.
And magnets have fields around them.
Invisible magnetic fields. We draw field lines from north to south. Closer lines mean stronger field. You can map them with a compass or see the pattern with iron filings.
Okay, electric quantities. Charge.
Measured in coulombs. Can be positive or negative. Again, likes repel, opposites attract, creates an electric field around it.
Conductors versus insulators.
Conductors, like metals, have free charges, electrons that can move easily. Insulators don't. You can charge insulators by friction. Rubbing transfers electrons.
Static electricity. Can you detect charge?
With things like a charged rod attracting small bits of paper, or a gold leaf electroscope where the leaves repel if it gets charged. Electric fields have specific patterns too.
Current.
Flow of charge, measured in amps. Amperes. 1 amp is 1 coulomb per second, IQ, Q.
Conventional current versus electron flow.
Conventionally, we say current flows from positive to negative. In metals, it's actually the negative electrons flowing the other way. DC is direct current, one direction. AC is alternating current, changes direction.
Measured with an ammeter in series.
Correct. EMF and potential difference, PD, both measured in volts.
Yes. EMF, electromotive force, is the energy per charge supplied by the source, like a battery.
Yeah.
PD, or voltage, is the energy per charge used by a component. V equals WQ, measured with a voltmeter in parallel.
And resistance, opposition to current, measured in ohms. R equals VI. Ohm's law says for some components, like resistors at constant temp, resistance is constant, so V is proportional to I.
But not for everything, like filament lamps.
Right. A lamp's filament heats up, increasing resistance, so the VI graph curves. Diodes only let current flow easily one way. Resistance of a wire depends on its length. Longer means more resistance. In cross-sectional area, thicker means less resistance.
What about electrical energy and power?
Energy is E equals IVT joules. Power is P equals IV watts. Electrical energy is often billed in kilowatt hours, kWh, which is a unit of energy, not power.
Circuits. Series and parallel.
Series, components in a line. Same current through all. Voltage from source is shared. Total resistance adds up. RT equals R1 plus R2.
Parallel. Components on separate branches. Voltage across each branch is the same. Current splits up. Total resistance is tricky. 4RT equals 1R1 plus 1R2. Adding resistors in parallel decreases total resistance.
Useful components like potential dividers.
Yeah, using resistors in series to get a specific fraction of the source voltage.
Yeah.
Like a volume control. Safety is huge with electricity.
Absolutely. Hazards like frayed wires, overheating cables, damp conditions, overloading sockets.
Mains electricity uses live, neutral, and earth wires.
Yes. Live carries the high voltage. Neutral completes the circuit near 0 volts. Earth is a safety wire connected to the ground. Switches and fuses go in the live wire.
Fuses and circuit breakers protect against too much current.
Right. They break the circuit if the current gets dangerously high, preventing overheating and fires. Double insulation or earthing metal casings protects users from shocks.
Now the link. Electromagnetism.
Induction.
Generating electricity from magnetism.
Oh.
If you move a wire through a magnetic field or change the field around a coil, you induce an EMF voltage.
What affects how much voltage you get?
Moving faster, stronger magnet, more turns on the coil, longer wire in the field all increase the induced EMF. The direction depends on the direction of motion and field. Fleming's right-hand rule.
This is how generators work.
Exactly. AC generators spin a coil in a magnetic field, or vice versa, to produce alternating current. Slip rings connect the spinning coil to the circuit.
And currents make magnetic fields.
They do. A straight wire has circular field lines around it. Right-hand grip rule. A coil, solenoid, makes a field like a bar magnet. Stronger with more turns, more current, or an iron core inside.
Yes. Putting an iron core inside makes a strong temporary magnet an electromagnet. Used in scrapyard cranes, electric bells, relays.
Loudspeakers use this too.
Yeah, an AC signal in a coil attached to the speaker cone moves in and out of a permanent magnet's field, making the cone vibrate and produce sound.
Okay, force on a current.
If you put a current-carrying wire in a magnetic field that isn't parallel to the wire, it experiences a force. Direction given by Fleming's left-hand rule.
This makes motors turn.
Precisely. A coil carrying current in a magnetic field experiences forces that make it rotate. A split-ring commutator cleverly reverses the current direction in the coil every half turn to keep it spinning the same way. That's a DC motor.
And transformers, changing voltage.
Use induction too. 2 coils wrapped on an iron core. AC, current in the primary coil, creates a changing magnetic field in the core. This changing field induces an AC EMF in the secondary coil.
Step up or step down?
Depends on the number of turns. More turns on secondary steps, voltage up and current down. Fewer turns, steps voltage down and current up. VPVs and dBs ends. Used in power lines to step voltage way up for transmission, reduces energy loss as heat, PIRER, and then down again for homes.
Okay, deep breath. Nuclear physics, the atom.
Right. Tiny, dense, positive nucleus with protons and neutrons surrounded by orbiting negative electrons.
Protons positive, neutrons neutral, electrons negative.
Yep. Atomic number Z is number of protons defines the element. Mass number A is protons plus neutrons. Notation shows A and Z. Neutral atoms have equal protons and electrons. Ions have gained or lost electrons.
Rutherford's experiment showed the nucleus was small and positive.
Alpha scattering, yeah. Most alphas went straight through thin gold foil, atom mostly empty space, but some deflected sharply, hit a small, dense, positive nucleus.
Isotopes.
Same element, same number of protons Z, but different number of neutrons, so different mass number A.
Yeah.
Like carbon-12 and carbon-14.
So nuclei are unstable.
Yes, leading to radioactivity or nuclear reactions like fission or fusion.
Fission is splitting large nuclei, like in reactors.
Uranium splits when hit by a neutron, releasing energy and more neutrons, which can cause a chain reaction.
Fusion is joining small nuclei, like in stars.
Hydrogen fuses into helium, releasing huge amounts of energy. That's the sun's power source. Nuclear equations must balance A and Z.
Radioactivity itself, how's it detected?
Geiger-Müller tube encounter is common, measures counts per second, Becquerel's BQ. There's always background radiation from rocks, cosmic rays, etc. We measure the source and subtract the background. Decay is random.
3 main types of radiation: alpha, beta, gamma.
Alpha, like a helium nucleus, 2p plus 2n. Positive charge. Big, slow, highly ionized, damaging, but stopped easily by paper skin. Beta, fast electron or positron, negative or positive charge, smaller, faster. Moderately ionizing, moderately penetrating, started by thin aluminium. Gamma, high energy electromagnetic wave, no mass, no charge, travels at light speed, weakly ionizing but highly penetrating, needs thick lead or concrete.
Ionizing means knocking electrons off atoms.
Yes. Alpha's best at it, gamma worst. Generally, more ionizing means less penetrating.
And decay happens because the nucleus is unstable.
It wants to become more stable by releasing energy and particles. Alpha decay reduces A by 4, Z by 2. Beta decay, electron emission, keeps A same, increases Z by 1. Gamma often follows alpha or beta, releasing excess energy.
Half-life.
The time it takes for half the unstable nuclei in a sample to decay, or for the activity count rate to halve. It's constant for a given isotope.
How is radioactivity used?
Depends on the type and half-life. Long half-life alpha in smoke detectors. Gamma for sterilizing food equipment, long half-life beta for thickness monitoring, short half-life gamma for medical tracers or cancer therapy.
Safety is key, though.
Absolutely. Ionizing radiation damages cells. Minimize exposure, keep distance, limit time, use shielding like lead, store radioactive sources securely.
Last stop, space physics, Earth, and solar system.
Okay, Earth spins every 24 hours day-night. Orbits the sun every 365.25 days year. Tilt of axis causes seasons. Moon orbits Earth in about a month, giving us phases as we see different amounts of its sunlit side.
We can calculate orbital speed.
If we approximate orbit as circular, speed is distance, 2 divided by time, period t.
The solar system, sun at the center.
Gravitationally bound system. Sun is the star, has most mass. Then 8 planets: Mercury, Venus, Earth, Mars, rocky inner, Jupiter, Saturn, Uranus, Neptune, gas giants outer, plus dwarf planets, asteroids, mainly between Mars and Jupiter, comets, icy bodies with long orbits.
We see planets by reflected sunlight. Light takes time to travel.
Yes, light speed is fast but finite. Takes about 8 minutes from sun to Earth. Distances are huge.
Data varies a lot between planet size, density, temperature, gravity.
Reflects their composition and distance from the sun. Orbits aren't perfectly circular, they're ellipses. Planets move faster when closer to the sun.
How did it all form?
Accretion model. Giant cloud of gas and dust, nebula collapsed under gravity, formed spinning disk, sun ignited in center, dust grains stuck together, grew into planetesimals, then planets. Temperature gradient meant rocky planets formed close in, gas giants further out.
Beyond the solar system, scars in the universe.
Sun is just one star. Billions of stars make up our galaxy, the Milky Way. Distance is measured in light years. Distance light travels in a year.
Stars have life cycles.
They do. Born from nebulae, become stable stars fusing hydrogen, like our sun. Smaller stars end up as white dwarfs after puffing off outer layers, planetary nebula. Massive stars go out in a bang supernova, leaving behind neutron stars or black holes.
Supernovae create heavier elements.
Yes, they forge elements heavier than iron and scatter them into space, ready for new stars and planets.
And the universe itself
Contains billions of galaxies. We observe that light from distant galaxies is redshifted.
Meaning the wavelength is stretched, like the Doppler effect for light.
Exactly. And the further away a galaxy is, the greater its redshift.
Huh.
This means they're moving away from us, and faster ones are further away. Evidence the universe is expanding.
Supports the Big Bang Theory.
Strongly. The expansion implies everything started from a single hot, dense point billions of years ago. Hubble's law, V, H-0, relates speed and distance. The Hubble constant lets us estimate the age of the universe.
Any other evidence for the Big Bang?
Cosmic microwave background radiation, CMBR. It's faint microwave afterglow from the early universe detected everywhere we look. Predicted by the theory, finding it was huge confirmation.
Wow, that's quite a journey. From basic measurements to the Big Bang.
It really is. And you see how the concepts connect forces, motion, energy, fields. They apply everywhere.
It really does feel like building a foundational picture.
Yeah.
Hopefully less overwhelming now for you listening.
We hope it sparks some insights, those aha moments we talked about. It's not just abstract stuff, it's how everything works.
And if something specific grabbed your interest, maybe astrophysics or quantum stuff, which we didn't even touch, there's always more to explore.
Definitely. So maybe think about how these laws play out around you every day. From making toast to looking at the stars, it's a fascinating world out there. Keep asking questions.